We went through this in the last round of lectures. There are 4 or 5 different control structures. These are structures that allow you to iterate through your codes. The first one is a for loop, while, and the third one is if. There's also do whiles and switch cases. So we'll talk about those. Remember, for loop has 3 elements inside. The first one is your conditional statement. So your initializations. So X has to be some sort of a counter with a numbering system. Typically, the counter starts with 0, but in some cases, it may start with a non-zero numbers. They're really never in a negative range, right? There's no reason for it. Y is a conditional statement. So this Y evaluates to true or false. Z is the increment or decrement for the counters. Remember that every single one of these statements ends with a semicolon. The second one is a while. This X is your conditional statement. So is the X for the if statement. One caveat as a best practice is to ensure that every time you have an if statement, you want to end it with a else, right? So that's just a best practice. Sometimes you don't need to have it, but it's not good to use if and then else if without an else, right? So you want to make sure whenever you have an if, there's an else. It is not an else if, but else, right, at the very end of that control structures. So here is an example of control structures in while loop. So what is wrong with the above? So let's take a look at it. The counter itself is 1. As long as X is not equal to 20, you're going to keep on printing it. The problem with this approach is, initially, the first iteration gives you X equals 1. So this is going to be printed because 1 is not 20. The second one is 3. X is going to be 5, right? So forth. And X is never going to reach 20, right? In this case, you're going to have a infinite loop. So how would you be able to correct that? Well, to be able to correct that, you want to ensure that you have some sort of condition that gives you or binds the entire problem space from an infinite space to a finite space. And the way to do that is using a less than or equal to, right? These conditional operators to ensure that your problem set is bounded so that it doesn't go through the infinite, go through infinities. So that's really also another best practice too, because you never know what your condition is gonna lend you to. So there's a lot of different types of scenarios where you lead to that leads to infinity or infinite loops when you have control structures like this. So just be super careful with it. Some of those specific circumstances may be very, very hard to debug, right? So in that case, you're going to have a situation where most of the time, let's say 99.9% of the time, you're not going to be able to, the code looks fine, but in that 0.1% of the time, you end up with an infinite loop that eventually may crash the whole system. So hopefully that system is not financial, because people could be losing money, right? So just be careful with the use of your control structures, ensuring that the best practices are in place before you deliver them. Okay. Here's another an example of what you may get. So starting with x equals 10, right? So as long as x is greater than 0, you can keep on going. So I won't get into the details. You should be able to have this in your console and see for yourself. You are most likely familiar with these already, but I'm going to go through it once more. So these relational equality operators are pretty standard operators in conditional statements. So in conditional statements where you have some sort of left-hand side, right-hand side comparisons, you will use these operators to to set your problem space. Either they are left-hand side, right-hand side equals to each other, not equal to each other, less than, greater than, or less than equal to, less than equal to, right? So these are pretty standard, and I'll bypass them quickly. Sometimes you may come across mathematical computations that are pretty long. So when you have situations like this, you know, we know all of the conditional operators we need to use, but sometimes we don't know the precedent. Let's say, you know, multiplication, this start has a precedence over equals sign, right? So in this case, you don't really need to, you know, have a parentheses around 2 times y. Sometimes you may have to, but you know, when you have a whole bunch of you know, plus, minus, modulus, how do you know which one takes precedence, right? Which operator has higher precedence than the other? In other words, the evaluation takes place on certain operators first prior to the other, right? This is where liberal use of parentheses around these operators and numbers or variables, so to speak, becomes very important. So let me give you a number of examples. Actually, I think I have a couple of examples in the later chapters. I'll go through them. Let me see. So yeah, so this is pretty straightforward. The standard operators, you know, plus, you know, minus, you know, multiplication, divisions. There is this thing called modulus. So this is the percent sign. This modulus gives you essentially the remainder of a division. So 11 divides, when 11 is divided by 3, it gives you the quotient, right? The quotient is 3, right? Because if quotient is 4, it'll give you 12, and that's not the answer. But the remainder, when you divide 11 by 3, is going to give you 2, right? Because while the remainder is 3, I'm sorry, the quotient is 3, the remainder is going to be 2. So modulus gives you the remainder, and it's a very, very commonly used operators in C, C++, and other programming languages. So typically use it, this modulus, to look for whether a number is completely divisible by certain numbers. So in that case, you know, if the remainder is 0, that means the number that you're using in the denominator is completely divisible. I'm sorry, the numerator is completely divisible by the denominators. Okay, so that's that. How would you be able to express this? So you should be able to write this up in C, C++, and see if you you can get the desired result. I wanted just to caution you, when you have a very complicated mathematical expressions, use these parentheses, closing these parentheses liberally as much as you can. There's really no best practices for it, but make sure that you know, sometimes we may have to take them out into different lines to ensure readabilities. All right, so like I said, modulus gives you a remainder of 2 when 5 is divided 5 is modded 3. So I think this is related to your break hash. When you have a value divided by 100, it basically tells you whether that value is it basically tells you whether that value is a multiple of hundreds, right? But when the value is modded by 100, it tells you whether the value is the multiple of 100 with some remainders at the end. One thing I wanted to mention, though, this was from your break hash assignment, and that is, what if value is a double or float? Notice that 100 is a integer, right? And then your result is in integers. What happens when your value is a double? Well, if the value is a double and when the double is divided by hundreds. So all of a sudden, if you think about this, the computer memory has 8 bytes, right? Memory space allocated for double, whereas integer is only 4 bytes. So 8 bytes is twice the amount of space as your integer. Your end result, either your remainder or quotient, is going to be double as well. Okay, so while let's say if value is a double, your value divided by 100 in this case is going to be a double. That's what happens on your right hand side. Now on the left hand side, dollar is an integer. So what happens is value divided by 100 is going to take place first. That's going to give you a double, and that double is going to be assigned. It's going to be assigned to an integer data types. So when a double, which is the 8 byte, is assigned to a 4 byte space, you're losing precisions. So all of the decimal numbers, they'll be gone. Okay, they're not going to be rounded right into the integers. So what you're left with is the integral side of your value, and all of the decimal spaces are gone. Okay, so same thing with the modulus too. Okay, if one of them is double, even if you do, let's say if assume value is an integer, but you change this 100 to 100.0, this gives you a double or float type. So when you do a mod, or even a value, when you're doing a divisions or a mod, the right hand side here is going to give you a double, right? Let's just assume you're changing 100 to 100.0. Okay, so we do this a lot. Whenever you have a increment, let's say a equals a plus b, you can do plus equal sign. So a equals a minus b is a minus equals b. So this is frequently used. We do that on multiplications. We do that on divisions. Also, we do that on modulus. This is a shorthand for a lot of things. Just remember that you don't swap the order of these things, right? Make sure that the equal sign is always on the right side, and the rest of the other operators on the left hand side of that compound operations. Okay, so far so good, and this is all just a review from I think lecture 5 or 6. So plus plus and minus minus, you'll be familiar with that. There is a difference between a prefix or postfix, or suffix or prefix increment or decrement operators. The problem with this is sometimes students don't understand the orders. When you have a suffix, this means that 8 minus minus is evaluated after this semicolon. When you have a prefix, let's say minus minus a, this minus minus decrementing a happens right on the spot as soon as this one is encountered, even before the statement is ended, right? So let's just assume a is 3. So in this case, b is going to be 3, right? Because this assignment, right, takes place when a is decremented, but this decrementation does not take place until the statement is over. But before the statement is over, the assignment takes place, right? So b equals 3, nothing happens. But in this case, on the prefix level, this minus minus 8 is evaluated right before the statement is over, right? And that evaluation is going to lead to a value of 2. 2 is assigned to b, so b in this case is 2, right? So these are two different things. Students get confused by it, but just remember, when you have your incrementing or decrementing operators before a variable, that action, right, takes place right on the spot. Okay, so that's what I want to say about the increment decrementing operators. So this is a pretty standard set of. You should have this in your high school or junior high school. These logical operators in C, C++, Pythons, and some of the other languages we use for AND logical operators, we use double ampersand. We use double pipes or, right? So you should understand true and true evaluates to true, right? False and true, false. So if either one of them is false, the AND operator is going to give you false. You pretty much have to be true, true on both sides to give you true. But or is either or, right? So true, true gives you true, true or false gives you true, false, true gives you true, right? So you should review these. Okay, so this is also frequently encounters. You use logical operators in conjunctions with some of the compound operators and also conditional operators on conditional statements. And this conditional statements sometimes could be very hard to understand. So it's better for you to, if you have a pretty complicated set of combination of different operators, you want to separate them in different lines. In this case, you want to also use the parentheses liberally when possible to avoid, to avoid readability issues. Yep. And just to remember that also logical operators have very, very low precedence. So it's pretty much guaranteed that, if you don't, if you have left-hand side, right-hand side, regardless what they have, they will be evaluated first prior to the AND operations. So in this case, we didn't really use parentheses around parentheses equals greater than 0 or parentheses less than 100, right? There's no need to create inner parentheses there to capture the precedence. Sorry. Same thing with this too. The OR operations has a very, very low precedence than the operations on left-hand side and the right-hand sides. Okay. All right. Okay, so we're gonna lead into this brand new topic of array. So you came across a couple of these before. There's different types of array. So array is a collection of data, right? Each of the data inside the array is of the same data type. Not only that, these types and these values are sitting in memory next to each other. So contiguous block of memory. So in this case, we know that if you write integer I3, this bracket 3 insinuates that there is an array of a collection of 3 integer elements inside this block of memory. And since you have 3 of them, each integer is 4 bytes. There's a total of 12 bytes. Okay, so each 12 bytes, each 4 bytes is going to give you a number, and they're basically sitting next to each other. Same thing with a collection of charts. So we know chart is 1 byte. So in this case, there's 3 bytes memory space, 4 bytes memory space. In this case, there's actually 4 bytes memory space as well. Why? Well, if you look at this, there is a difference between C++ style and C style string. This is actually a C way of writing string back in the 60s or early 70s. This is how you would create a string in C, right? We're not talking about C++, so in C. And this thing looks very curious, right? So if you recall, every time you have a double quote around a collection of characters, that is considered a C++ string, right? But you have to remember, during the early 70s, C++ didn't come around until the late 70s, right? So this notion of using a double quote for C++ string did not exist at the time. So this is a C way of creating a string. And why did I say this is 4 bytes? Well, if you look at this, there's a collection of 3 characters in there, E, D, and U, right? So back in the days, for creating C-style string, you also have to include what's called a null terminator. So the very last byte, the fourth byte, is for storing that zero, that null, N-U-L-L, okay? But anyway, so this is how you would create a C-style string as opposed to a string array. So when I say string, typically in today's language, string means C++, okay? C++ string. So just recall that C++ string is a class. Creating a classic or any C++ string takes up about 24 bytes. So since you have an array of 3 C++ string, this is 24 times 3, right? The amount of memory that you need. Now, let me just quickly go through this. Even though string is a C++ concept, internally that string class uses what's called the char array as well. So string is a class that wraps around the C-style string. So internally, the string buffer that stores the individual characters of 1 byte each, it's also used in C++ string. You just don't see it, okay? What comes with the C++ string class, just a whole bunch of properties and behaviors or functions that you can invoke on a string, C++ string instance.